Hola Mauricio, ¿puedes decirnos, puedes anotarnos en el chat si se escucha bien? Ay, apenas está entrando. Sí está ahí, ¿no? Se lo acomodamos. Sí está ahí.
Porque no está hoy, después contesta en la sala de espera. ¿Intentas ayudar? Pues,
Sí, 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 sí. Dile que no.
La sala de espera.
Ajá.
Ah, no, pero habilitar la sala de espera es que ellos esperen, ¿no? Para darles el acceso, ¿no? Entonces es deshabilitar.
y no, es que no uso Zoom.
Digo. Hola Mauricio, ¿puedes comentarnos si se escucha bien en el chat, porfa? Es que el micrófono para saber si se escucha bien el micrófono, porfa.
El
¿Lo
micrófono ya
presentas?
está abierto.
Sí, hola a todos.
No sé si está el apuntador conectado.
Espérame.
¿Qué necesito? Ah, claro.
Ya. Ya se escucha. Le preguntamos a Mauricio si se escucha.
Buenas tardes. Gracias por estar aquí en la sesión. I'm very pleased to introduce the next speaker. He's Juan Omar Gómez with his talk, Tensor Triangular Geometry in Context. Please go ahead.
Again, your introduction, please. Thank you.
Yeah, so I you say that first I will thank the organizers for the invitation. I'm excited to speak about this topic since I think this theory is beautiful, and I hope to convey part of this idea through this lecture series. And let me start just by maybe trying to give you a content of this. Maybe this is not important at this moment. But in order to give you motivation, let me make first a convention. And I will use TT as an abbreviation for tensor triangular or tensor triangulated, depending on what suits better the context, okay? And let me explain you what TT geometry is about. So as defined by Paul Barmer, who is the person who invented this theory, is the study of the categories, the algebra geometric methods. So basically, one has TT cats arising from different contexts in pure mathematics, let's say algebraic geometry, or maybe algebraic topology, representation theory, and so on, right? And the whole point of this context of TT geometry is to offer you a unified framework to study any of these categories. And the whole point of this is that you maybe have the chance to mix and match techniques and methods using any of these specific contexts and apply to a different one. And also you obtain like a really general tools that you can apply in a specific scenario. So in particular, one of the, let's say, of the most important invariants that we have is something that we can associate to any essentially small TT cat, which is called the Balmer spectrum. And this Balmer spectrum goes from a TT cat to TT geometry. So this spectrum gives us some geometric intuition about our category. In particular, it encodes some parameterization of our objects up to certain equivalence. Well, okay, maybe this makes any sense at this point, but the point of this lecture series is to clarify all of these terms. And for this, let me start with one of the first things that we need to at least understand, that is, oh, I'm sorry, the title's in Spanish, but it's triangulated categories. And since I just assume that not all of you are familiar with this topic, I'll decide to give a crash course on this topic. So basically, the notion of a triangulated category is due to Verdier. He was studying the derived category of an abelian one, and he basically isolated the main properties that the derived category has to, let's say, be able to speak about derived functors in a more general set. And well, let me start then with the definition of a triangulated category. Oh, well, maybe let me also make another convention. I will not write the convention, but I will just say it, that I will always assume that my categories are locally small. But well, a triangulated category for us will be a triple like this, where C is an additive category, sigma is an autoequivalence that is often referred as the suspension functor. Well, I'm assuming that this autoequivalence is an additive functor. And it comes equipped with a distinguished class of triangles. Or, well, distinguished or exact are just the same thing. What's a triangle? Well, a triangle is just a sequence of this form. So you can write something like this. The suspension of X. And one of the first axioms that I'll ask is that this class is closed under isomorphism. What it means is that if you have any other triangle, right, X prime, Y prime, Z prime, sigma Z, sigma X prime, right? First of all, a morphism of triangles is just a collection of maps of this form. Let's say this is F. This has to be the suspension of F, such that these three squares are commutative. And you say that this triangle is isomorphic to this triangle if each of the maps here is an isomorphism. So we ask our distinguished class of triangles to be closed under isomorphism. And this triple has to satisfy the following axioms. So the first one is that we can always, or we will always have this triangle, which is the identity of X, right, for any element in your category. So this will be always a distinguished triangle or an exact triangle. As I say, it's just the same thing. And the second one tells us that we can always rotate our exact triangles. So basically, if you have a triangle like this, you can rotate it to the left. And note that here we're using a sign, just because in practice that's useful. But since I'm saying that this is an if and only if, it means that I can also rotate triangles to the right. And just keep doing it. So the second one is that if we have a partial morphism of triangles, meaning, well, of distinguished triangles, meaning that if I have something like this partial, meaning that we only have two maps, and this, oh, this is horrible. We have two maps such that this square is commutative, then the axiom tells us that we can always complete this to a map of triangles. So there exists a map here such that the three squares are commutative. And we don't ask this map to be unique, so it only has to exist. So the third axiom tells us that any morphism in our category fits into an exact triangle, meaning that if we have something like this, right? Y, then we can always put it into something like this. Okay, well, this is T2, T3. And let me try to motivate the following axiom, which is referred as the octahedron axiom, and is somehow tells you that if you have two composable maps in your category, so if you have something like X, Y, and set. So you have two composable maps, right? So this is the composition, G followed by F. And let's say like you can extend this first map into an exact triangle, and just to make things a bit suggestive, then you write this into this form. So the third object in my distinguished triangle would be G mod X. So I can do the same here, right? And I have set mod Y. But now here I have X mod, set mod X. So I have this diagram, and this octahedron axiom tells us that we can always find these arrows in such a way that this is commutative, and also this is an exact triangle. And you can see this is some sort of an isomorphism theory. That's why I wrote the third elements in my distinguished triangles this way, meaning like if you take set mod X mod Y mod X, what you obtain is set mod Y. So maybe this is a bit overwhelming, but I will give you some examples, and that's the whole point of this. Like I'll just introduce a series of examples, and hopefully you have encountered one of those in your life. All right. So, but before that, let me just give you some easy, well, relatively easy consequences that we can deduce out of these axioms. And the first one is that if we have an exact triangle of this form, we can always guarantee that the composition of two, well, of course, composable maps is trivial. And just maybe to convince you that it's not that hard, let me give you a proof of this. This is a bit easy, right? So you have your distinguished triangle, and you want to check that G followed by, F followed by G is trivial, then you can do something like this. So you take X, take the identity of X, and here you have G, F, I'm sorry, right? So this square is commutative. Just note that is F and F. This is a distinguished triangle by my first axiom. So I can complete this partial morphism of triangles. And since this has to be commutative, then it tells me that F followed by G is the same as going from X to 0 and then to 0 to set. So it's trivial. Now, one also has that the functors given by homing out from A and homing into A send exact triangles to long exact sequences of abelian groups. So this first functor is known as a nomological functor, and the second one as a cohomological functor. I will not explain much of this, but let me just write a bit of this. So if we have an exact triangle like this, right? What it tells you is that if we have something, well, I'm writing a lot the same triangle, I'm sorry, but that's how it is. So if we apply the functor hom A blank, so of course this functor is the functor, so sorry, these homs are my hom groups in C, and we obtain a long exact sequence of this form. So hom A X, and this map is induced by F, right? So this hom A to Y, and so on. Hom A to Z. And now the whole point of the axiom that tells me that I can rotate my triangle either to the left and to the right tells me that this exact sequence go for the to the right and for the to the left. So it's just an unbounded complex of abelian groups. Yeah? Well, I will not prove that this is actually exact, but you know, just the first property tells me at least that this is actually a complex, right? Because if you compose, you have to compose basically F with G, which we already saw that is the zeromorphism. So we also have a version of the 5 lemma. And let me explain a bit what this means. Maybe I will use this part. So it basically tells us that if we have two exact triangles like this, x prime, y prime, z prime, suspension of x prime. And if we have two maps, let's say alpha and beta, which are isomorphisms, then gamma is an isomorphism as well. How do you prove this? Well, we can use home, right, in C, for instance, apply to this triangle. So since this is a functor, we obtain bounded acyclic complexes of abelian groups in top associated to this exact triangle. We obtain one in the top, and we have connecting maps, which makes everything commutative. And the point is that there we can apply the 5 lemma for abelian groups. So basically it tells us that this map here is an isomorphism as well. So now the map induced here by this morphism is composing with gamma. So if we take the unit here, it means that we have a map from Z prime to Z such that composed with gamma is the identity. And you can apply the reverse to find the other side inverse of gamma. So use these and the 5 lemma for abelian groups. Yes. Oh, so if you have let's say, a 5-term exact sequence, right? So if you have, I don't know, x1, x2, x3, x4, x5, something like this, right? Which is exact. I mean, exact, I mean here, right? Here, here, here. And if we know that these maps are isomorphisms, then this is also an isomorphism. So we're applying this to these home groups. Yeah. So now we can apply this version of the 5 lemma to actually guarantee that our third element in any exact triangle is determined by the first map appearing in this exact triangle. Meaning that if we have something like this, f to y to z sigma x, right? And then we have the same guy, meaning we have f, but now we have a different object here, z prime. Then we can always use the identity here, right? The identity here, and this is, of course, commutative. So our actions tell us that we can complete this partial morphism of triangles into a morphism of triangles. And now the version of the 5 lemma tells that then Z and Z prime has to be isomorphic, sorry. The whole point of this is that, as you noticed before, or as I already stressed, is that the map that exists that completes this morphism is not unique, which means that the map here that makes Z and Z prime isomorphic is not canonical. So the warning is that, oh, well, since this is unique, let me just establish some notation. So we can just say that in any exact triangle, we can always denote the third object as something that makes reference of F, the first morphism, and we often call this the cone of F. So this cone of F is well defined, but the point is the cone is not functorial. So this is actually some kind of defect of triangulated categories, and there are different ways to get around this problem, but we will not touch any of that. So one of the other properties that one can obtain out of these axioms is that, for instance, a map is an isomorphism if and only if its cone is trivial. which is nice. I will not prove it, but feel free to try. And if you get stuck, you ask me. Sorry. One can also prove that direct sums of exact triangles is an exact triangle. And moreover, if one has an exact triangle of this form and the map H is trivial, then my object Y, sorry, has to split, meaning that it has to be the direct sum of X and Z. Again, since I can rotate my triangles, you can really just assume that any of the maps, if any of the maps, sorry, is trivial, then my triangle has to split. And this is also an interesting exercise and prove that any mono in my triangulated category is split. So now I guess it's time to speak about examples. I guess this is maybe more enlightening that just give you a bunch of actions and properties that you can obtain out of it. So let's consider an abelian category. Yeah. So the typical example would be left modules over a ring, the ring with unit and associative. I'm not brave enough to consider more general rings. Or you can consider chiefs on a scheme. So we can consider the category of chain complexes, meaning that maybe I will use this part. Use it to establish some notation. Let me say that a chain complex or chain complexes will have homological grading. So it's a sequence of this form. Where differentials D such that the objects X to the N are elements in our category A. These are maps in our category, and such that the N followed by the N plus 1 is trivial. So this is a chain complex. Again, this homological grading. And a map of chain complexes use a family of maps in our category, making this diagram commutative. So you have Fn, Fn plus 1, Fo, Fn plus 2, and so on. So again, a morphism between the complex, let me just call this a complex X, and this will be the complex Y. So a map between X and Y is, as I say, is a collection of maps in our category, making this diagram commutative. So now actually, this category of chain complexes remains abelian. That's something interesting. But anyways, one sometimes is interested in weaker notions, like maybe we want to identify objects up to homotopy or homology as well. So the category of chain complexes might not be suitable for the task. So one has to go to the homotopy category. And use, to define this, is the category with objects chain complexes, but we change the morphisms between two chain complexes. So now we take or homomorphisms in the category of chain complexes, in the homotopy category of A, sorry, between two chain complexes, X and Y, will be the morphisms in the category of chain complexes, but up to homotopy. And we say that two maps are homotopy if there is, are a homotopy equivalent if there is a homotopy. A homotopy is something like this. Sn plus 1, such that, let me just say, so F is homotopy equivalent to G if and only if, by definition, exists this collection of Sn, right? These maps, such that their difference, F minus G, it's equal to dn plus 1, followed by Sn plus 1, plus SNDN. Okay. Maybe if one needs to make emphasis that this is the differential associated to y, one writes something like this, but in order to make the notation a bit, or to use the notation, just let me forget, and hopefully it's clear from the context. So now the point is that this homotopy category is not longer abelian, at least not in general. Yeah? So for instance, another exercise is that one can check that the homotopy category of abelian groups is not abelian. So maybe this is not trivial, but the hint is use the property H. Sorry, 8. So use that any mono splits. But for this, of course, since this property is for a triangulated category, let me tell you how we can consider the homotopy category of A as a triangulated category. So I'll spell out the structure that you need. And the first thing that we need to specify is an autoequivalence of Ka. And this is given by the shift of chain complexes. Since I'm not sure if you have seen this before, just let me make it concrete. So the shift of chain complexes is given as follows. So if you have something like a complex, chain complex X, so you need to specify what are the objects in each degree. So let's say in degree n is xn plus 1. So in other words, we shift our complex to the left. And our differential, so now the differential of x shifted by 1 in degree n, well, it's just the same as the differential of x, but now in degree n plus 1, but we also add a sign here. So this, of course, will be an autoequivalence. You can just basically shift to the other side to obtain the inverse of this functor. And let me tell you what are the, or what is the distinguished class of triangles, and is any triangle that is isomorphic to one of this form. And let me just tell you what this means. So basically you start with a map of chain complexes, F, and you construct this mapping cone, which is X shifted by 1 direct sum with Y. And now the differential of this map, let me tell you what it is. I hope this doesn't make any confusion, but I will just omit. It's the differential of X. Maybe it's worth to say what it is. So it's minus the differential of n plus 1, the differential n plus 1 of X. My map F in degree n plus 1, 0, and the differential of Y in degree n. So this is the differential. And let me tell you what the map I is. And just by the definition, we're using Y as a direct sum of this mapping, the mapping cone. So we can use I as the inclusion in the second component. And now P will be just a projection in the first component. So anything that is isomorphic to a triangle of this form will be a distinguished triangle. And with this structure, one can verify that this is actually a triangulated category. Let me give you another example of a triangulated category. And this example works for any Frobenius category. But let me spell out this Frobenius category in my favorite scenario, which is in modular representation theory. So if we fix a field K, a positive characteristic, and a finite group, and if you are familiar, you can consider a finite group scheme defined over K. It's fine. And one often assumes that the characteristic of the field divides the order of the group. So one can consider the category of KG modules, left KG modules. If you're considering the group scheme, then you take the algebra of measures as KG. But well, the point is, sorry, I mean, here I'm considering just finally generated KG modules, okay? And one consider the full subcategory on projective modules. And one can perform the following construction, which is called the stable category of KG modules. So by definition, the stable category of KG modules is the additive quotient of the category of finally generated KG modules, not the projective ones. Let me tell you what it means. So you keep the same objects, but now the morphisms are identified if they factor through a projective. And now this guy has a triangulated structure given as follows. So the suspension functor will be determined by, well, in objects, by taking, for instance, a projective cover of or object M, and then taking the kernel. So the kernel of this surjection onto M is what the functor omega does to objects. And one can check that this is well-defined up to projectives. So in other words, it's a functor that is well-defined in the stable module category. Basically here, one is identifying projective modules to 0. That's why this is well-defined. And well, one can use like the universal property of these projective objects to extend this construction to maps. So it's a functorial construction. So this is the suspension functor. And if you want to know what's the inverse, is basically you take a module, you embed this module into its injective hole and take the cokernel. So that construction gives you an inverse for this. And what are the distinguished triangles? Well, the distinguished triangles are induced by good old-fashioned short exact sequences of KG modules. So you take your short exact sequence, you can basically project it to the stable module category, and up to certain things, anything that is isomorphic to that will be a distinguished triangle. Well, these things are a bit too algebraic, maybe, and just to give you, or to convince you that this setting is really general, let me give you an example of something that doesn't have that algebraic flavor. This category? Well, that's a good question. At some point, I think people just call it that way just because, I don't know, they wanted to invert the functor. But if you want something conceptual, is that you are actually inverting in a universal way your functor omega. So it's stabilization. But yeah, I think that wasn't the motivation. I think just people called it the stable category. Yeah, as I say, just to give you an example of something that is not algebraic. Actually, you can formalize what it means for a triangular category to be algebraic, but I will not say it. But anyways, this category is not algebraic in that context. So it really has a different kind of flavor, and it's topological flavor. So this category is the Spanier-Whitehead category, and it consists of finite pointed CW complexes, and you take morphisms as stable pointed homotopy groups. I will not say what it means, just because it's a bit complicated, but let me just tell you what's the triangulated structure that you can give to this category. And I will tell you this with some kind of draws, and I'm really bad, so I apologize in advance. So so if we have let me just say the suspension. If we have a space X, right, its suspension is something that is known as the reduced suspension. Oh, sorry, they are pointed, you have a base point, and eventually perform its ordinary suspension, but you now also identify this line, right, that goes through the base point. So this is the suspension, and what are the exact triangles? And the exact triangles are things like or things that are isomorphic to the following construction. So you basically take something that is called the homotopy cofiber of this diagram. So you basically construct the cone of X. This is the cone of X. And you glue this cone of X via F to Y. So this is the pico. So yeah, anything that is isomorphic to that will be a distinguished triangle. This is also known as the homotopy category of finite spectra. I mean, as I say, it's used to give you or to justify that this can be applied in a much more general setting, not just algebraic categories. Okay, now I will want to talk about Verdier quotients, and just because I want to give you another example that is relevant for us, which is the derived category. So for this, let me define what an exact functor is between triangulated categories, and it will be an additive functor which commutes with the suspension and sends exact triangles to exact triangles. So an example of this is that if you have an additive functor between abelian categories, then you can extend this functor pointwise to chain complexes, and these will send homotopies to homotopies. So you obtain an induced functor between the homotopy category of A to the homotopy category of A prime, and this will be an exact functor. So the second example will be if you take a subgroup of H of G, then the restriction will induce an exact functor between stable categories. Okay, now let me say what a triangulated subcategory is. And if we take D a full subcategory of C, we say that D is a triangulated subcategory. It satisfies that for any exact triangle of this form, if any two of the three elements appearing in this triangle are in D, then so is the third one. Yeah, for instance, if X and Y are in D, then Z has to be in D as well. This basically gives you that this category D is closed under suspension of C. And it also has a class of distinguished triangles induced from the distinguished triangles of C. So in other words, we have that D is a triangulated category itself with this induced structure. So we can say now that, well, basically a triangulated subcategory will be one of the form that, it's a triangulated category such that the inclusion functor will be an exact functor. Okay. And there is something that probably I mentioned that from now on I will assume that all my triangulated subcategories are replete, which means that they are closed under isomorphisms. Okay, we're almost there. Now let me define what a thick subcategory is. So it will be use a triangulated subcategory, which is closed under retracts. What it means to be closed under retracts is basically if you have something, if you have an object that can be written as the direct sum of two other objects, let's say X and Y. So if this is in D, then it implies that both X and Y are in D as well. So now an example of a thick subcategory is that if you consider an exact functor between two triangulated categories, then the full subcategory of C on objects such that are mapped to zero via this functor is a thick subcategory of C. It's an easy exercise. You can try it. And these categories refer as the kernel of F. So now we have arrived to the definition definition theorem of a Verdier localization or a Verdier quotient. And it tells that if we have a T subcategory of C, then, well, then it always exists a category that is denoted as C mod I, an exact functor Q from C to C mod I, satisfying the following universal property. This universal property tells that if we have any other exact functor from C to D, of course, I'm assuming that D is also triangulated, such that the kernel of F is contained in I, then F has to factor through Q. Let me draw this diagram. So if you have we have a functor to C mod I, so this is Q. And now we have another functor F, which kernel is contained in I, and it has to exist a unique exact functor from C mod I to D. So of course, I'm assuming that this is good. And this construction, or well, this category C mod I, is often referred as the Verdier quotient. And somehow it tells that we can take quotients, right, of triangulated categories by thick subcategories. And actually, if we have, well, if you are familiar with these localizations, triangulated categories, you always, let me say this in a different way. So one can also check that the kernel of this quotient is actually I. And that's why I'm assuming that this is thick. You can drop the thickness of I to the expense of not having that the kernel is I. Not that important, but now we have arrived to the following remark, and is that if an object in C is mapped to the trivial object in this quotient, in C mod I, then the object has to be an I. It's just consequence of what I wrote. And now, in particular, one can think of this category as some sort of inverting maps which have cone in I. So there is an explicit way to describe this Verdier quotient. So you keep the same objects, and now you say that a morphism is something that is a roof. I will not explain it, but there is a way to define explicit this Verdier localization. In this case,
Kernels are, can I identify kernels with thick subcategories?
well, localizations on thick subcategories, yeah. So if you have a thick subcategory, you can consider this exact localization, right? And if you have an exact localization, you can obtain a thick subcategory by taking its kernel.
It has to satisfy.
A localization, yeah. So yeah, so like studying thick subcategories of C is the same as studying exact localizations of C. So we have arrived to what I wanted to say today, and it's define the derived category of A. And again, if we take A to be an abelian category, one can consider the full subcategory on acyclic chain complexes. What is chain complex that is exact everywhere? And one can check that this subcategory is actually a thick subcategory of the homotopy category of A. And if we have this in mind, then one can perform, or one can use Verdier's theorem, right, to construct the following category that is known as the derived category. So by definition, it will be the Verdier localization of Ki by the acyclic complexes. Okay. So this is nice, just spelling out. Maybe you have heard of this derived category. And one often says that the derived category is obtained from the homotopy category by formally inverting quasi-isomorphisms. And that's what you say. So, well, again, right? You have a chain complex. Right, you have your differential, Cn plus 1, we can define an abelian group, which is called the homotopy, the cohomology of X, degree n, to be the kernel of dn+1, dn mod the image of the n-1. So the definition is that our chain complex is cyclic if it has no cohomology. So this is trivial, where, well, maybe let me see, I for all I. Okay? And one often says that a map F from X to Y is a quasi-iso if it induces an isomorphism in homology. Well, in homology, since my convention of the gradient. So if F, or well, let me just say HF from Hn of X to Hn+1 of X is an isomorphism for all I. And now one can verify that, well, this will be an exercise. F is a quasi-isomorphism if and only if the cone of F is acyclic, meaning that the cohomology of, well, again, EI of the cone of F is zero. So the whole point of this is to just clarify that we're doing the same as maybe the definition you will find in other scenarios. Yeah. Thanks. Yeah, I'm sorry. Has to be in the same degree. Use the functor Hn to Y. Thanks. So yeah, we are formally inverting quasi-isomorphism in this construction of the derived category of A. One can also talk about derived functors. I will not do that this time, but just let me tell you about certain relevant subcategories of Ki, and those are denoted as K plus of A, K minus and Kb, and they're basically the full subcategories of Ki, where we only consider things isomorphic to bounded above complexes, meaning that if you take, so K plus of A, so you take the objects here, so you take complexes such that Xn is trivial for n sufficiently large, so you can define dually K minus, and K bounded, you take all the complexes which have only finally many non-trivial cohomology groups. Okay, and one can perform the same definitions for the derived categories. What's the point of this is that you can check that with this definition, these categories are triangulated subcategories of Ki. So that's it. Thanks.
You mentioned that the cone construction was not factorial, so you mean from the arrow category to the category itself? Or?
Yeah, for instance, well, one can make this explicit, right? So Well, yeah. What I was trying to say is that yeah, you can always have x f to y, right? And this you have the cone, right? And well, of course, you can associate it also, right? Yeah, so the arrow category, so you have x prime, so y prime, right? F prime. So to the cone of f prime. And as you say, well, you can complete it in a non-canonical way. So now what's the problem is that if you take as definition, right, that the map between these two cones is this map, then you can never prove that that this construction respect composition.
But did you get that map to do? Sorry, what the time? Yes.
This map is well defined, yeah. But it's not close under composition, so it's not functorial. This assignation is not functorial.
Like maybe you get time.
Yeah, but I mean, you need to ask for or more structure on your triangulated category in order to make that. Certain sense, yeah. I mean, it's not that easy.
And my other question was, so when you define that in that category, the portion of the category, by the secret complexes, so you say you have a bunch of the secret complexes that are not homotopy.
Yes, so we are making that difference, so thanks, yeah. So of course, in the homotopy category of A, something is trivial if it is chain homotopy to the zero, right? So the complex that has zero every. But if you have a chain complex which has no cohomology, it doesn't mean that it's contracted, like it is homotopy equivalent to the zero. It's a big distinction. Thanks. Okay.
¿Ya está el audio abierto? Sí. Sí. ¿Perdón? Ahí. Sí, ya está todo. Ya te están escuchando y viendo.
Thanks. We continue again with the next speaker. It's Rosas with from Morelia University. Please go ahead.
Thank you, organizers, for inviting me to this event. I'm going to talk about Williams conjecture and proof one. So, the talk is divided into 4 parts. First, I'm going to give some preliminaries. Then I'm going to talk about Lorentz rings and marks. Then I'm going to give some things about finite posets, and finally, I'm going to talk about the posets and the Williams conjecture. So, work preliminary. We will be working with finite groups, finite sets, finite posets. So, if I say group, is a finite set. So, we have a group G. Set X is the G set. We have an action of G on X, either on the left or on the right. So we are going to work with left axis. So our G sets are going to be left G sets. And the examples that are very interesting are we have a group and X and Y G sets. Their disjoint union and their Cartesian product are G sets. This is going to be important. And okay, we have G sets and how we can relate. If we have X and Y to G sets, the mapping from X to Y is a morphism of G sets if it respects the action. So with this, we can form the category of G sets. The subjects are G sets and morphisms as this. That's all about preliminary. So we're going to continue with words and rings. But first, we have these things. So we have a group, H a subgroup of G, and X a G set. So the set of fixed points of H and X is going to be denoted by X to the H. And we define the mark of H on X as the cardinality of this set, and is denoted by P H of X. And I'm going to call this as H mark of X. Okay, we have some properties about the marks. So the mark, the H mark of the disjoint union is the sum of the marks. The mark of the Cartesian product is the product of the marks. And if we have 2 subgroups of G that are conjugate, their marks are the same for G sets. Okay. And we have an important theorem that is the Lorentz theorem that says that 2 G sets X and Y are isomorphic if and only if their marks are the same for any subgroup of the group. So the marks characterize the G sets. And Now we can find the Bornstein ring of a finite group G as the graphemic group of this category. So it is the 3G module generated by the isomorphism classes of finite G sets modulo this subgroup that gives us the sum on the Bornstein ring and is a ring with the multiplication given by the Cartesian product on the generators. It is on the isomorphism classes of the G sets. And a consequence of the Bornstein theorem is that, okay, it is, the Bornstein ring is a commutative ring with identity, the isomorphism class of the single point. And it has basis, as basis, the set of isomorphism classes of the transitive G sets. Moreover, if we remember, transitive G sets can be represented as a quotient, like this. So the Bornstein ring as abelian group can be seen like this direct sum. And whereas B is a set of representatives of conjugacy classes of subgroups. Okay, that's all we need to know about Bornstein rings. So I'm going to continue with finding posits. Okay. And I'm going to talk about homology of posits. So if we have a posit, a finite posit, and if we take a natural n, we can denote the set of chains of elements of x of cardinality n plus 1 as SNX. With this, we can construct a chain complex that we'll denote as this, as the complex of the modules defined, well, the module Cn of x is the 3D module with basis this set of chains. And the differential is given by this formula, where this xi hat represents the vector without the I entry. We take this entry. Okay, and the n-homology group of the chain complex is denoted by Hn of x and is called the n-homology of the poset. And we can also define the other characteristic by of the poset as this alternate. Okay. If we have two posets x and y and have an order preserving map, there is an induced map of chain complexes given by this thing. And well, if we have again two posets x and y and two more order preserving morphisms f and l, we will say that f is homotopic to L if for every natural there exists a morphism of the modules that the sum of compositions is the difference of these maps, as Ponomar said last. And we will say that X is contractible if the identity of the poset is homotopic to a constant map. A corollary of the definition of homology is that X is contractible if it has the homology of a single point. It is with this coefficient. It is Z if n is equal to 0 and 0 otherwise. Okay. Another definition. If F and G are maps of posets, so this notation means that in images the order is preserved, and we will say that two morphisms of posets are comparable if F is less or equal than G or G is less or equal than F. And this theorem is important for the next part, And it says that if F and L are order-preserving morphisms from X to Y and are comparable, then they are homotopy. And this is all about finding deposits, and we will continue with deposits. So if we have find for G, a deposit X is a G set that is also a poset. And the action and the order relation are compatible. Again, we have objects. Now, what about the morphisms? If we have two deposits, X and Y, a morphism of deposits is a mapping that preserves the action and preserves the order. And now we can define this invariant that is useful for work. So if we have a deposit, then the set of chains of length n+1 is a G set with this action. And when X is finite, we are working with finite deposits, we can define the Lefschetz invariant as the element of the Born-Set ring of G that is this alternate sum. Actually, this Sn of X is itself an element of the Born-Set ring.
So is this the first time you need X to be finite? Or did you need it before to be defined homology?
We can find homology for any.
Right? So
This is the first one we did find. And for the following, we need to define. Okay. Properties of the Lefschetz invariant. We can see the Lefschetz invariant as a G set. And we can take the fixed points of this. And it is again a Lefschetz invariant, but this in another Born-Set ring. It is in the Born-Set ring of this group is the Y group. So the fixed points of a Lefschetz invariant is this Lefschetz invariant in this Born-Set ring. If we take the mark, the H mark of the Lefschetz invariant is the Euler characteristic of the set of fixed points. And if we have the two Lefschetz invariants are the same in the Born-Set ring, it happens if and only if their Euler characteristics are the same. And this is for any subgroup H of G. Okay. We will say that G poset is G acyclic if this poset is acyclic. It is that the homology of this poset is D is equal to 0 or 0 always. And we have this proposition that if we have X and Y G posets and two morphisms of G posets, one from X to Y and the other one from Y to X, and this composition is comparable to the identity of X, and this composition is comparable to the identity of Y, then their Lefschetz invariants are the same in the Born-Set ring of G. And if a G poset has a biggest element or a smallest element, then it is contractible. Moreover, it is G acyclic. Okay. So let SP of G denote the poset of non-trivial p subgroups of G. And Quillen conjectured in 1978 that if we have a finite group and the prime that divides the order of G, then the geometric realization of SP of G is contractible if and only if G has a non-trivial normal p subgroup. We can see the poset of non-trivial p subgroups of G as a simplicial complex with the simplices, actually the Sn of, of, of this one. So we have the one, this conjecture is actually, some mathematicians have been working on this conjecture, and in this year, in March, Antonio Diaz Ramos published a preprint where he solved the conjecture for all of primes, and Kevin Peterman is working on this conjecture for the prime two. So it is still open. But I'm going to give a weaker version of this conjecture that is merely algebraic. So, okay, this is the poset of non-trivial piece of groups is a poset, but this is a G poset with on which G acts on biconjugation, and we have this theorem that the Lefschetz invariant of this G poset is the identity of the Barnes ring, if and only if there exists a non-trivial normal piece of group. And this result is fundamental for the following theorem, but first I'm going to give this definition that G poset is G contractible if for every subgroup of G, the set of fixed points is contractible. So if we have a finite group and a prime that divides the order of the group, then the Lefschetz invariant of SP of G is the identity in the Bronsted ring, if and only if G has non-trivial normal P subgroup, if and only if SP of G is G contractible. And with this, we have a weaker version of the conjecture, proven weaker version of it. And yeah, this is the bibliography. In this chapter, we can find a lot of information about Barnes rings. In this book, we can find a lot of information of Barnes rings and bisequential for groups. And this is the preprint of Antonio Diaz Ramos. This is the original article where William stated this conjecture, and
Thanks. Any question? Oops.
Maybe this is a stupid question, but in Quillen's conjecture, is it obvious for simple groups? Like when
because Antonio Diaz Ramos worked on that.
did he go through the classification of simple groups? Okay. And do they think is correct? Is there like a consensus if the proof is, you don't know? Okay. Okay. Thanks.
Thanks.
So I was distracted. Could you show again which is the definition on SPG? Because I have the SNX, but because you say it's a G poset. Okay. Okay. It's just that I didn't see how was the order, what was the order, but now the order is the inclusion. Yeah. Okay, thanks.
Thanks. Any question? No? We Thanks. Pues sí, creo que hoy ya estuvo, no sé.
Ah, sí. Nos vamos a tomar una foto acá abajo. Esa es, ¿no?
So thank you so much. See you tomorrow.
Pero esto ya lo ordenamos una vez.